Electrical installation testing. Introduction to the module. This module details all the recommended tests and procedures that should be initiated during or after installing electrical equipment to ensure the efficiency and safety of the appliances provided. Topics to be covered in this module: the protective conductor continuity test, the insulation resistance test, protective conductor and touch current measurements, ring final circuit test, polarity test, earth electrode testing, prospective fault current test, functional checks, substitute leakage test, load test, flash testing. The protective conductor continuity test. This test is primarily carried out to ensure that the protective conductor is working correctly and that a valid connection exists between the conductor and the earthing. It should be carried on equipment that has protective earthing itself. One of two types of the test should be carried out. 1. Low current test. This is a continuity measurement that possesses a short circuit test that lies between 20 mA and 200 mA. 2. High current test. This is a continuity measurement that uses a short circuit test current that will go as high as 25 ampere, but not exceeds that value. In both procedures, the test should be made between the earthed metal part of the equipment and the plug's earth pin. Certain factors will affect your choice between a high or low current test. The high current test is best performed on equipment that allows a solid connection to be made to conductive parts with the test probe. This may quickly identify an earthing issue by showing a failure or heating up and causing a rise in resistance measurement. Due to its nature, it is not appropriate for IT-related devices or sensitive appliances. The low current test is recommended for equipment that has protective earthing connections, but not an exposed conductive part. This may be a device with plastic casing and with the output leads, providing the only conduction. However, the low current test may give incorrect results if used on cordless devices or appliances with no clean external metal parts. Some modern IET testers are designed primarily for low current tests, but will emit a high current pulse at the start of a test to overcome any contact resistance and these inherent problems. Others may also reverse their initial polarity to provide more accurate results. Low current tests are generally considered to give accurate readings for earth connections and will provide perfectly good results at either 100 mA or 200 mA. Testers should still consider high current tests in some situations, however. If possible, the resistance testing should be applied whilst the cable is being flexed, and all unusual variations should be checked. In the case of the value continually rising, this will be caused by a poor connection gradually heating up. If there are multiple conductive parts to an appliance or piece of equipment, then multiple tests will need to be performed to ensure they are earthed safely. Ensure the test lead is always touching a conductive part, and not a connection or assembly part, nut, screw, etc. As mentioned in earlier modules, IT equipment such as PCs or laptops may be earthed only for functional purposes, and a high current test is not appropriate or required. Always take care to place the lead against the right conductive points, as contact with alternative earthing points, signal cable, etc. can cause incorrect readings to be taken. When recording the results, some limits and values should not be exceeded. This simple table will give some guidance, where the located sign is less or equal to, and omega is ohm. Other essential points to consider during the testing are: metal parts covered with paint or dirt may give incorrect readings on occasions. Make sure that your test probe and conductive points are as clean as possible. Some older equipment may have slightly higher protective conductive continuity values. A high rating of up to 0.5 ohm is acceptable in this case. Only carry out high current testing for as long as it takes to get a stable and consistent reading, with allowance for cable flexing time. Be aware of the accuracy of your test instruments. Borderline, maximum or minimum readings should be recorded as failures. You can calculate the resistance, R, of a productive conductor if you know the length and type of cable being used. Some basic test instruments, with simple pass or fail indicators or LEDs, may fail when used on equipment with long cables. In this case, instruments with numerical displays are recommended. With portable Class I equipment, it may have accidentally a thing caused by close contact with other nearby equipment. Check for this and ensure only exposed conductive parts are tested. If a batch of identical items is being tested, the readings should not deviate by much, and any anomalies should be further investigated. An insulation resistance test is typically instigated by applying 500 volt DC across the live conductors and the protective conductor. The resistance is then measured for an expected value. This voltage level may not be appropriate for some sensitive equipment, and testers are advised to either use a voltage of 250 volt DC or measure the productive conductor and touch current. Live conductors are connected together for testing, with a special adapter being used to allow instruments to check polyphase equipment. The best way to ensure correct readings is to use a dedicated test instrument on a dedicated test socket. Testers must ensure all adapters and connections are removed before equipment is put back into service. Prior to testing, the equipment should be turned on, with all covers in place. The test is carried out between the live conductors and the equipment's main body, or the protective conductor. The testing equipment should sustain a test voltage of with a load resistance of 0.5 megaohm, and the values should not be less than those shown below. Other points to take into consideration during testing are: catering and heating equipment may not initially meet the expected readings due to necessary insulation or sheaths. These may need some rest time to allow accumulated moisture to dry off before testing. The line and neutral equipment should be connected before testing. This can be achieved by plugging the instrument into a special test socket or using an automatic pre-wired instrument. Some test instruments may not have this ability, but a quick check on a test plug can verify this. If a test between the neutral and earth pin does not result in a failure, the instrument is not appropriate for use, and an adapter should be utilized. Some Class II equipment may only need a visual inspection to ensure that the insulation is still effective. This is at the discretion of the duty holder. If testing is required, it should be implemented with the probe touching conductive or buried points accordingly. With equipment that contains SPDs, surge protection devices, or similar safety features, a test voltage of 500 voltage may be dissipated and give lower readings. In this case, or with sensitive equipment, it is perfectly acceptable to run the test at 250 voltage DC, as this will not trigger the SPD and will still give accurate readings. Protective conductor and touch current measurements. A protective conductor and touch current test may be appropriate in conjunction with an insulation test on the equipment. These are tests that originally come from manufacturing compliance procedures and require certain conditions and dedicated test circuits. The process can be carried out by measuring the flow in a protective conductor or the flow in the live conductors. Results will depend upon the manufacturer's instructions and other factors. Appropriate results will likely be supplied by the manufacturer themselves. Ring final circuit test. The purpose of this test is to ensure that the cables form a complete ring without any unnecessary interconnections between the wires, and the polarity is correct on all outlets. The test will also measure both the live and earth conductors' resistance together, R1 plus R2, and identify spurs that may exist on the ring. A typical ring circuit will be wired in 2.5 mm square phase conductor with 1.5 mm square CPC, circuit protective conductor, as the recommended size. This is an A1 ring and has a 30 or 32 amp overcurrent protective device. For a complete ring circuit, the test is carried out to ensure the conductors form a complete loop to prevent possible overloading. With some facilities that have more than one ring circuit, they can become entangled with two protective devices supporting just one ring. The main objective of a ring circuit is to maintain a high current from small CSA, cross-sectional area, cables, with two or more often being wired in parallel. A 2.5 mm square cable will carry at least 20 amps, and if two conductors are used in parallel, the carrying capacity will be raised to 40 amps. This is acceptable because the protective device is smaller than the capacity of the cables in parallel. If a ring of this type is broken, it may stop the protective device from working as it is rated 32 amps, and a single cable is only 20 amps, which may cause overloading issues. On occasions, an internal ring may be intentionally added to a ring circuit, making an interconnection for specified uses. Note that if one loop is broken on an interconnected ring, the whole circuit may still show as operational, so multiple tests must be carried out. All sockets must be checked before the testing, otherwise, serious issues could ensue. If the phase and neutral are of the wrong polarity, neutral could be switched in at any point. If Class 1 equipment is in use, the live conductors with the reverse polarity and cause a potentially deadly shock. As it is considered to be a dead test, the circuit must be isolated. A low resistance ohm meter must be used and set on the lowest scale, usually 20 ohms. Make sure the instrument is 0 ED or the lead's resistance is calculated before testing is started and the readings are taken. Polarity test. A polarity test is instigated to primarily confirm that all single-pole devices, fuses, switches, and circuit breakers are connected in the phase conductor only. Accessories, like cooking units, should also be checked for connection status during testing. If the work is being carried out on a consumer unit or distribution board, it should be safely isolated. The readings should be taken on a low resistance ohm meter and can be initiated during the same testing period as a CEC continuity check. When performing polarity testing on a radial circuit, cookers, immersion heaters, etc., find the start of the circuit, use crocodile clips and a lead to link the phase and CPC together. Make sure the phase conductor is identifiable by color and attached to the protective device. Remove the utility switch at the furthest point of the circuit, confirm the presence of the phase conductor, and connect into the right terminal. Null the leads of the instrument if the value is needed for resistance measurement, R1 plus R2. Connect the leads of the test instrument to the incoming CPC terminals and phase at the switch. Test the continuity now, and you should receive a very low value, equivalent to R1 plus R2. Remove the lead from the consumer unit and attempt the test again. This time the reading should be high and indicate the circuit is open, giving accurate values. When performing polarity testing on a lighting circuit, at the start of the circuit, use crocodile clips and a lead to connect together the phase and the CPC. Go to the ceiling rose or lighting fixture and place the instrument's test probes to the earth wire terminal and switched live. If you close the switch that controls the light, you should get a low reading on the instrument, R1 plus R2. When you open the switch again, you should get a high value on the instrument. A polarity test on a lighting circuit can also be performed at the switch itself, in which case, link the phase and CPC as usual with crocodile clips and a lead. Open the switch. Take the test probes from the instrument and place them on the earth terminal and the switch return terminal. Close the switch and you should see a very low resistance rating displayed on the instrument's screen. Open the switch and the instrument's display should be either very high or over a measurable range, as the circuit should now be open. When performing a live polarity test, which is normally instigated to check that the right power supply is being delivered to an installation, the instrument used should be a voltage indicator or a test lamp, which comply with British standards and HSE regulations. An earth loop impedance meter may also be used. The voltage indicator test probes are placed on the phase and neutral terminal of the incoming supply on the main switch. At this point, it should indicate a live supply. Now place the indicator's testing probes onto the phase and earth terminal of the incoming supply at the main switch. Again, it should indicate a live supply. Now place the indicator's probes onto the earthing terminal and the neutral terminal of the main switch. This time no supply should be indicated. Earth electrode testing. Earth loop impedance testing is used to check that, if a fault occurs in an electrical installation, there will still be enough current to operate a fuse or circuit breaker, which protects the faulty circuit. For most installations, the resistance of an earth electrode can be measured with a dedicated test instrument. It can safely be used on many types of systems where high resistance values can be expected. To carry out the testing, make sure the installation is isolated. Make sure the earthing conductor is correctly terminated at the earth electrode. Disconnect the earthing conductor completely from the earthing terminal. Connect one lead from the test instrument to the earthing terminal. Place the testing probe from the instrument to the phase conductor found at the supply side of the switch. Perform the test and record the results. Reconnect all disabled connections and leave the installation in good working order. When referencing the readings, the maximum permissible resistance value of an earth electrode is 50 by I delta N. This may look like a complicated equation, where 50 equals maximum voltage and I delta N equals the trip rating of a residual current device. But it basically means that exposed metalwork should not carry a voltage potential of more than 50 voltage. For equipment with a rating of 100 mA, this means that the absolute maximum value would be 500 ohm. 50 by 0.1 equals 500. However, atmospheric conditions and humidity mean variations, so the preferred value for reliability is 200 ohm. All maximum limits are. Prospective fault current test. A prospective short-circuit current is the maximum amount of current that could flow between a phase and a neutral, or between phase conductors. A prospective earth fault current is the maximum amount of current that can flow between live conductors and earth. The largest of these values will become the prospective fault current of an installation. Testing is usually carried out alongside earth electrode testing, with the values being measured and recorded in kA, kiloamps. The testing is applied between the phase and the neutral, and can typically be found by either measuring, calculating, or checking with the supplier, who will tell you the maximum PFC. To carry out the test, use a prospective fault current tester and ensure you are familiar with the manufacturing instructions. For 2 lead instruments, set the instrument to PFC. Place the instrument's testing probes on the phase and neutral terminals, which can be found at the main switch's supply side. Press the test button and record the readings that are displayed. For 3 lead instruments, put the phase lead on the main switch's supply side and the remaining probes, or clips, on the earthing terminal. Press the test button and record the readings. Functional checks. Functional checks confirm the equipment's operational ability, with the emphasis on switches, isolators, and circuit breakers. These must be checked in unison to ensure they have been installed correctly and undergo any necessary optimum performance adjustments. The instrument normally used for this testing is an RCD tester, residual current device. It measures how long it takes for an RCD to interrupt the flow of a current and delivers a final value that is sized in milliseconds or seconds. Several types of RCD may be encountered. Voltage-operated, also known as voltage-operated earth leakage circuit breakers, ELCBs. BS4293 general device. BS4293 type S. BSN610081. BS7288. BSN610091. BSN610008 type S. Some RCDs, such as ELCBs, are no longer in active use and do not comply with current BS regulations. They do not functional testing, as they should be replaced if found in a system. Functional testing is performed on live systems, and appropriate care should be taken when applying them. To perform testing on a system with a BS4293 RCD, the RCD tester should be plugged into a local socket close to the RCD itself and set to its default tripping rate, typically 30 mA. It should then be set to 50% of the tripping rate, in this case, 15 mA. The test button should be pressed, and the RCD should not trip. All RCD test instruments have a specific switch that allows all testing to be done on opposing waveforms, from 0 degrees to 180 degrees. This switch should be moved to the opposite side of its current setting, and the test performed again. The RCD should not trip again. If it does trip, do not automatically assume the RCD is faulty. Check for leakage and low insulation resistance, and test again. After successfully completing those previous steps, set the test current to the full tripping value, in this case, 30 mA. Perform the test again. This time the RCD should trip within a time of 200 milliseconds. Confirm this and reset the RCD. As per the previous testing process, turn the waveform switch to its opposite value. Repeat the test, and the RCD should trip again within 200 milliseconds. Reset the RCD again. Note the two results from the test, and record the slowest time on your test results sheet. Now set the test current to 5 times the tripping current, in this case 150 milliamperes. Perform the test, and the RCD should trip within 40 milliseconds. As per the previous steps, turn the waveform switch to its opposite value again, and perform another test. The RCD should trip again within 40 milliseconds. Following the completion and documentation of all test results, you should ensure that the integral button on the RCD is pressed and that you have complete verification that the working parts are active and fully functioning again. The system is labeled with confirmation that the test has completed on this calendar date and that the user or operator should press the test button on at least a quarterly basis from this date onwards. Note: the exact same procedure can be performed on a BSN610081 RCD, but the tripping time on a 100% test will increase to 300 milliseconds. Performing a test on a BS4293 Type S. As this type of RCD has a time delay, there will be a pause before it actually trips during testing, which should be considered. Plug in the RCD tester close to the RCD. Set the instrument to the RCD trip value, ensuring it is also set to Type S. Test at 50%, and the RCD should not trip. Repeat the test with a different waveform. Set the test current to 100% and repeat the test. The RCD should trip at 400 milliseconds, 200 fault plus 200 time delay. Repeat testing on the opposite waveform. Record the slowest operating time. The same testing routine as performed on the BS4293 Type S can be applied to the following RCDs with the stated amendments. BSN61008 Type S. The device has a time delay of 200 milliseconds and a tripping time of 300 milliseconds. BS7288 RCD protected socket. The tripping times are the same as a BS4293. BSN61009 RCBOs, the same as a BS4293, with the following caveats. 50% test. Both waveforms. No RCD trip. 100% test. Both waveforms. RCD trip within 300 milliseconds. 5x test. RCD trip within 40 milliseconds. Substitute leakage test. The substitute, or alternative, leakage test is designed to measure the leakage current in an earth conductor, typically using a low AC voltage. It was intended to reduce the chance of electric shocks, and does not require the equipment to be in operation during the testing. It will deliver a resulting value that demonstrates the worst leakage current at the highest operative voltage limit. When checking Class I equipment, the phase conductors are joined together, as per normal PAT testing. 40 voltage of test voltage is then passed between the phase conductors and the protective conductor connection on the equipment. If Class II equipment is being checked, then the test lead and the probe of the testing instrument are directly connected to the appliance that is being tested. With the testing probes safely applied to the equipment's conductive parts, the true voltage is then measured at the socket, where the appliance is plugged inches. From these readings and results, the earth leakage current can be calculated with reference to the appliance supply voltage, and it can be determined if any technical issues remain. Load test. Sometimes called the operational or volts or ampere test, this procedure will measure the energy consumption that running equipment or appliances use. This is often used to represent an appliance's efficiency level, as the maximum volts or ampere load gives a good indication of this. Most appliances have a load volts or ampere limit, and this should be noted for testing purposes. When an IET tester performs a load test, this will determine that the assets are functioning normally, and current volts or ampere rating of the equipment. It will typically highlight any future or imminent issues, like a worn belt on a washing machine, which will affect a volts or ampere rating straight away. A tester should take care when performing load tests, as shocks can be passed by equipment that is not adequately grounded. If high leakage currents are confirmed or suspected, then an appropriate warning label should be displayed by the power connections. Flash testing. Flash testing is used to measure the leakage current of an appliance and uses high voltage test levels to achieve this 2500 volt to 3000 volt. It can be harmful to equipment, so is generally only used after repair work or during stress or safety testing, and not for in-service items. Summary. The following points have been covered in this module. High or low current tests can be performed on protective conductors to ensure that they are working correctly. Insulation resistance tests can be performed at a lower voltage level to prevent damage to sensitive equipment. If an interconnected ring circuit has a broken loop, it may not be immediately detectable, and multiple tests will be required. Polarity tests on lighting circuits can be performed from the switch or on the ceiling rose itself. Functional checks require 50%, 100%, and two waveform tests to be applied to ensure the RCD trips in good time.